Hi everyone, meteorologist Gary Woodall here, and welcome to this episode of the Mid-South Weather Musings. In this episode, we're going to talk about weather radar, one of the important tools, electronic tools, for observing and detecting thunderstorms and precipitation. Stay tuned, episode's coming right up. Weather radar is, without a doubt, one of the most important electronic tools that we have when trying to detect thunderstorms, severe thunderstorms, really any type of precipitation that's in the area. There are some important characteristics, though, some important things we need to keep in mind when looking at weather radar data. We also need to have a little understanding of just how the radar works, how it generates some of this basic data that we have and that we look at. So let's get into some of these secrets of the weather radar. So how exactly does weather radar work? Well, as the antenna spins around, the transmitter sends out a very short burst of radio waves, somewhere around a microsecond long, these bursts of radio waves. Those radio waves will travel out from the antenna at the speed of light, 186,000 miles per second, until they hit something, a raindrop, a hailstone, or a snowflake, for example. When that happens, a very small portion of the radio wave is returned back to the antenna. That's called an echo. So the radar system keeps track of the direction that the antenna was pointed. It keeps track of how long it took those radio waves to make the round trip from the antenna to the target and back to the antenna, so it can calculate how far away that target was. And then it uses that information to plot an echo. And those individual echoes are what make up the radar imagery that we see. And the radar system will repeat this process about 1,000 times a second. Pulse and listen, pulse and listen, pulse and listen. And again, that information from these multiple pulses and multiple listening periods is what goes on to generate the radar imagery that we're all familiar with. Now, there are a couple of important considerations with the radar data. The first is what's called beam spreading. We need to remember that the radar beam is not just like a pencil line coming out from the antenna. The beam is actually shaped more like a very, very thin pie slice. So the beam will actually spread out, get wider as we get further away from the radar. In fact, the beam will expand almost 1,000 feet for every 10 miles that the beam travels away from the radar, from the antenna itself. So at 60 miles, the beam is over a mile wide, and at 120 miles, the beam is over 2 miles wide. And this has some important implications when we're looking at thunderstorms. As basically, the closer a storm is to the radar, the higher resolution look the meteorologists are going to get at that storm. At close range, the meteorologists will be able to see very small scale signatures and features associated with a storm. But at a long range, a long distance away, some of those smaller features may just get smeared out by the fact that the radar beam is so wide. Another important issue is the height of the beam. In addition to the spreading, this pie shape to the radar beam that we had just talked about, we also need to remember that the beam does not travel in a perfectly straight line. The angle of the lowest elevation slice is typically a ½ degree above the horizontal. So as the beam goes out, the Earth will be curving away from underneath it, and the beam will be climbing slightly as well. Also, differences in air density will affect the path of the beam as well. This is called refraction in the atmosphere. But the bottom line, if we have normal refraction conditions and with this ½ degree slice, at 30 miles away from the radar, the center of the beam is going to be about 2,200 feet above the ground, pretty close to the height of the cloud base of the storm that we're looking at. And at 70 miles, the center of the beam is going to be around 6,500 feet above the ground. So yes, radar is a tremendously helpful electronic tool, but because of these considerations, storm spotters play a very important role, especially with storms that are a longer distance away from a radar. Now, there are a lot of different types of weather radars that are out there. Some of the media, the TV stations have radars which are very good, very highly capable radars. What we're going to talk about here is the baseline National Weather Service radar, which is called the WSR-88D. This is what forms the National Doppler Radar Network across the country. And it is a Doppler radar, so it can measure not only where is the precipitation, but how are those targets moving that the radar is detecting. And we'll talk about that here in just a little bit. There are also a number of computer algorithms, computer programs built into the system that help in analyzing the data, looking for areas of potential hail or potentially large hail, estimating rainfall, looking for areas of rotation, and these algorithms help with analyzing the storm. Now the radar, the 88D, uses what are called volume scans to sample the atmosphere. And here's a typical volume scan, this diagram here at the lower right. The radar does a low-level slice, and then the antenna will tilt up a little higher. We'll do a little higher slice, the antenna will tilt up higher, and so on to get a three-dimensional look through the atmosphere in the area of the radar. And for each one of these slices, we'll get two of our base parameters, reflectivity and velocity. We'll talk about those in just a minute. We also can get derived products for each of the volume scans when the volume scan is completed. And this would be, again, the rainfall estimates, hail probabilities, and the like. Now, it takes about 5 minutes or so for the radar to complete this volume scan. And we need that information for looking up in the storm and seeing what's going on up there. A lot of times when severe weather comes down to the ground, it has its beginnings up in the thunderstorm. So finding out what's going on up in the storm is important. The downside, though, is that we would only get one of these half-degree low-level slices about every 5 or 6 minutes or so. But there was a recent upgrade to the WSR-88D called SAILS, which will basically stop the volume scan, maybe a third or halfway through, come back down and do an extra low-level slice, and then resume the rest of the volume scan. And this gives, instead of maybe every 5 or 6 minutes, can give us maybe every 2-minute or so low-level slices. And that can be very important when severe storms are coming through. So a couple of the fundamental data images that we get from the radar. This is reflectivity, and this is the regular weather radar display that you're probably used to seeing. It's basically a measure of how much power, how much of those radio waves from the bursts that go out from the antenna were returned back to the antenna. Reflectivity is measured in units called dBz. It's a logarithmic scale if you're interested in that. What is important, though, is that all the radar images will typically have a color scale off to the side to show you what color what dBz value is represented by what color. And there are two main flavors, two main types of reflectivity that you may see on your app or the website that you're looking at: base reflectivity and composite reflectivity. Base reflectivity, like we show here on the left, is a single elevation slice, one of those individual slices that we looked at on the volume scan diagram. And oftentimes with the websites and the apps, it'll be one of the lowest few slices that you can look at. Base reflectivity is important for looking at some of the structure, looking for some of the signatures that might suggest a strong or severe thunderstorm. The other flavor that you might be able to see is called composite reflectivity. Composite reflectivity will plot the highest reflectivity value, the highest return, anywhere through the depth of that volume scan, anywhere through the depth of the storm. And so this is a composite reflectivity is a good first look at potentially strong thunderstorms, kind of a first little heads up. But composite reflectivity is going to mask some of those structures and some of those signatures that might suggest severe weather, a severe storm is in progress. So composite is a good first look, but the base reflectivity is necessary for looking at the more detailed structures. Now, since the WSR-88D is a Doppler weather radar, it can actually measure radial velocities, velocities toward or away from the antenna. And in this case, the radar is right here where you see the red dot and the blue KNQA. The folks that designed this scheme were pretty clever in that they made the reds, the warm colors, the reds, the oranges, and the yellows, indicating outbound motions or out away from the antenna. The greens, the blues, the cool colors represent motion inbound or in towards the antenna. And then the clever part, the brighter the color, the higher the velocity. So easy to sort of pick out some areas of high velocity in these images. Now, there will often be some areas of purple, like we see in here and off to the west and a little bit to the northeast of the radar site. And that is, its official name is range folding, and that's basically the radar system saying that I cannot give a reliable velocity estimate here, so I'm just going to color it purple and say I don't know. Now, one important thing to remember about Doppler velocity data is it can only measure, we can only see motions toward or away from the radar. We cannot see motions that would go across the radar beam, perpendicular to the radar beam. And that makes looking and interpreting velocity images a little challenging sometimes. So in some future episodes of the Musings, we'll dive more into weather radar. We'll take a look at some basic reflectivity interpretation, some basic velocity interpretation, some of the signatures that we would want to look for. We'll take a look at reflectivity signatures that might suggest a potentially strong or severe storm. We'll take a look at the rotation signatures in the Doppler velocity data as well, and some of the terminology that's used when describing these rotation signatures. And then we'll talk about dual polarization, an important upgrade about 4 or 5 years ago to the WSR-88Ds. We'll talk about the idea behind dual polarization and some of the important data that is available, that it provides. So that's going to wrap it up for this episode of the Mid-South Weather Musings. If you like this information, this type of material, then follow us. If you're watching on YouTube, be sure and subscribe to our channel. If you're watching on Facebook, like and follow our page. That way you'll be notified when we send out new episodes of the Musings. If you have any particular topics that you'd like to see, mention those in the comments section. We'll see if we can work them into a future episode of the Musings as well. But again, thank you all so much for watching, and everybody keep safe.